Okay, guys. So yeah, then just get up. I just made sure I um cover that problem so that I can sleep at night, so that you guys have experience with it. Um, so now chapter 8 finally start, right? You'll do it today. You'll start today and you'll finish today. Okay, so let's just talk through what. This is some slight introduction. So by the way, I've not used, well, if you model structure, you use one Mises and these other theorems as well when you're looking at these principal stresses, and basically some of them use the stresses, some of them use energy theories to assume something fails, like at a specific energy limit. But I have not particularly used this chapter or even this chapter out of what I've loved to do is really remove it and do like bolts or fasteners rather, or welds and rivets. It's a more practical thing, I think. But yes, it is what it is. Not something I'm not really a fan of. It's just I haven't used it, and I don't know. We'll just kind of go through it, but fairly easy. Anyway, so we know forces applied to elastic material. You change its dimensions or inherent. Yes. If none of the stress exceed the elastic limit, the strain energy will be released when it is restored to its original dimension, and therefore it's able to do work. So that's quite interesting. So you deform the material, and actually, basically what we're actually doing is that it's actually getting the material storing energy. Funny enough, and once you release it, obviously it goes back. So you never think of that. You always just think it's gonna go. Like you never thought of it as energy. You just thought as obviously you're pulling it and then it was just going back. But actually, there's energy. That energy, when it's, I guess, when it's at the elastic limit and going back, when it's restoring itself, there's strain energy induced within the thing. So that's the idea. Then also there's something called the proof resilience, and that's the maximum amount of strain energy a material can absorb without permanent deformation. And we'll talk about that here, what that actually is. So there is a limit, and hence it can define the quantum strain energy absorbed in the material up to its elastic limit. Obviously, that is like the obvious thing. Obviously, was after that it's going to break. So the figure here on your, because it's swapped around, sorry, on your the modules of toughness now, but the modules of resilience, which is on the far left, that's what this for the proof resilience essentially. That's the amount of energy you can absorb before the rupture. Or sorry, that's the proof resilience. And what's important of that is that obviously we're looking at different material tensile graphs and stuff. You can actually see basically one material is more resilient than the other one. So yeah, so it's important to note that for whatever reason. Also the model is resilient is the maximum amount. And going back to the graph, so it's basically the whole area under that curve over there. And yeah, and then they also call it sometimes the modules of toughness. So it's nothing really what's particularly important, but that just kind of reach into something called toughness is the ability of material's ability to absorb energy before fracture. And we're going to talk about the large area of the tough material. But then what's important of this is that what tough is essentially defined as it's a combination of strength and ductility, right? So, when we talk about something tough is not the same as of course, in strength and materials domain, tough is not strength. So, toughness is an ability, is a combination of strength and ductility. Now, there is an application, I was thinking of this actually yesterday. I was impact testing, and obviously, I worked at a company where I was responsible for the materials lab, and obviously I never did any computation. So you just take a specimen. I don't know if you ever heard of an impact test before. It basically has an anvil, it swings, breaks the specimen, and then we record the amount of energy, and then it has a specific energy threshold. So I would say that's an application of it, but I haven't used any of the computations within that. But yeah, so I'm not sure toughness ability without failure various loads. I wouldn't say that really. It's not that. I don't agree with that definition. It's really about that curve, your stretch and strain curve, and the bigger that curve is, the more tough it is, and that's really true. I've tested like stainless steel impact test. And obviously this is at normal temperature. This stuff is very tough. And obviously as you really decrease the temperature around like -20, they become brittle. I've seen it happening. I've done it myself. So anyway, I just thought, should I introduce it? It's not really, I haven't done any of the computations within this. So yeah, just, that's okay. No big deal. All right, so what I wanted to actually touch on was, I wanted to just provide you awareness. The chapter itself talks about direct stresses, right? And what we'll be looking at is just direct stresses. However, remember what I mentioned to you, there's different loading types, and each loading type essentially can induce, right? Not induce, but I guess that they can store substrate energy. So there are some models there which I'd like you guys to just play around. So what I just basically did here was just I got the formulas for you, and unfortunately, it's the chapter only deals with direct stresses, but I'm just kind of expanding your mind to be aware that whether you have direct load, obviously tension and compression, or you have a shear load, or when you're bending, bending a beam or ruler, you're inducing strain energy. Likewise with torsion, when you're twisting something, you put the strain energy in. Obviously, this is now below so-called the resilience level or whatever. So what I just wanted a small exercise just to make you aware. So can we just get on? You got to use the models over there. So obviously the models are fairly simple there. You have to do the integral of anything. But let's find. So you've got a steel bar. It's got a cross section there, diameter. So cross section, circular cross section. Yeah, it's important. Diameter of 0.2, length. Got your modulus of elasticity and your modulus of rigidity. Let's see how much strain energy is or the body have when it's subjected to a tensor load, torque, uniform bending moment, shear force. Can we just quickly get this value? So just use those formulas and then just give me those answers. Obviously, the answers will be choose. I just want to expand your mind a bit, and it's going to be interesting to see here. And then you might ask, why am I doing this? Let's see what's going to store more strain energy, right? And this is not a fair comparison, especially with the bending moment of 25 kilonewton a meter. But I just wanted to show you something. It's obviously there's a radius and all of this, and yeah, let's just have fun. Okay, let's see a tensor load quickly. Stress squared, sigma squared, divided by 2E times volume of the bar. Is that's for the tensor load? You guys all get that one? The minus got energy of 0.0956. Yep. Next one, someone else maybe. No, chapter 8. So in this case, you have to use shear stress, and I guess, yeah, the area is still fine for shear as well. well, we're assuming basically single shear here. So for the shear force moment, torque, what energy do I get? So we torque, you gotta use this guy. Yep, that looks good. Yeah, torque. There's a lot more strain energy than 49.74. I hope that is torque. And if you look at these formulas, I just want you to really be aware of their properties, like there's A and E, A and G, or not properly, well, E and I, G and J. These are very important properties in stem cell materials. Your I, which we'll be touching on the next chapter, second amount of area, it's analogous to your inertia, rotational inertia, elastic modulus, your modulus of rigidity, your shear modulus. Very important stuff. The bending moment, what do we get? What do you guys get for the bending moment? 38.25. Yeah. 38.258. So then it's fine for shear as well. But yeah, so what I'm just illustrating you with is that you're typically going to find that, and yeah, it's 25 kilonewton is not essentially equivalent to 25 kilonewton meter bending moment, but yeah, 0.248. Yeah, but yeah, that's what I'm looking for. But what you're typically going to find is that more energy is stored, or strain energy. What was it, 2 something? 248 is typically stored in these. So torque loads and bending moment loads are somewhat of no real joke. And if you can force something, it's you're really inducing a lot of well, I guess you can store a lot of strain energy through torque and bending moment. There is a field called smart materials where they play around with these things as well. But yeah, so that's an interesting thing to show you guys that we're only dealing with number one in this particular chapter. And even with all these strain energy counterparts, you can actually with these formulas, you can actually find deflections. You can move. It's very powerful formulas once you know how to use them. But we're just going to use the first one. Nevertheless, okay. So the first part of this so-called this chapter, which is quite strange, they're talking about this, is that they talk about different loads, right? And the load here, what they talk about is a gradually applied load. So let's say gradually applied load increase from 0 to P at a constant rate. So the stress to material remains constant. This is normally done in a tensile test. We have a specific strain rate. But what it talks about is just that the strain energy is basically it's the area under the curve there, which is tension and load. It's nearly like the same as springs in a way, if you remember the spring formulas. And then just to play around the equation, they say U equals P times change in length, and then they just take those equations, essentially just plug them in there, and then you end up with P squared R over 2AE, which is essentially this formula over here at number 1, P squared R over 2AE. Of course, from that they extract it, they pull out the area, the length, and then you find the volume. Then they introduce 2 new concepts or 2 new so-called parameters, which is called the proof of resilience of a material, right? Which is the strain energy, which is equal to the same thing. And then the sigma squared divided by 2E, that is now called the so-called modulus of resilience of a material. That's just coming out of it. So that's now what we need to just know is that I'm looking at something here. We've talked about, what's supposed to be really mentioned there is we have a gradually applied load, right? And then we're going to have something called an impact load. And based on the analysis on top, the example they basically use is that you have some bar with a coil at the bottom and you drop a load, and what happens is it's known as an impact load or a shock load, and then they're just giving you a new model which is basically using potential energy there. So P, it's basically potential energy converted to strain energy. So it's P open brackets H plus change in length, obviously equals that, equals the strain energy we just got before, and then that's that. And then from this, they essentially come with a new model of if you have a shock load, you use this equation. So P over A, open brackets 1 plus or minus. Talk about that now over 1 plus 2A HE over PL. So what we are normally assuming in our computation is that the load was applied gradually, right? This is the standard thing we're assuming. So what happens now if the load is not applied gradually, but I guess a shock load or by impact, the stress as the new stress must be computed using that model over the P over A 1 plus whatever. Okay. And then the last one is just a live load, which is probably the most suspicious thing I've ever seen. And what they assume is that to find a live load, it's just 2 times your standard gradual thing. So we say, oh no, we're just going to times by 2 and it's going to be a live load. I don't particularly agree with this because I've seen tables depending on loading conditions, civil engineering tables. It depends. If you're on a bridge and there's constant traffic, that has a specific factor, specific loading. Do we call it a UDL when all the cars are on and obviously when it's moving, but the load is obviously changing. So I'm not sure exactly, but the idea is, yeah, when they say H goes to 0, they're just showing that model there, which is the H was here, basically H plus, and then that is 0, and then just end up with that formulation, which they call a live load. Live load is a suddenly applied load. Yeah. So it just touches the component, as what they say. Okay. So in summary, that's basically all you have to know. And what's important is you just be using different, like I said, this chapter, yeah, I'm not a big fan of this chapter. Doesn't feel right. I don't know. It's just put in the book, I think, just to give you more work. But yeah, those are the models you must know. Gradual applied is what you know. Suddenly you've got 2 times that, and then you've got your impulsive load where you've got this whole big shebang of a big model for assuming that. Oh yes, back to the impact load. So you've got 2 centers, a plus and a minus. So on impact, you get a tensile stress basically, and then on the rebound, basically. So I'd rather say the instantaneous tensile stress, basically when it's on impact, and then the negative value you get as a compressive stress basically on the rebound. And the thing is like, guess the rebounding is as it says, and it's that basically that value is typically ignored. So like I said, this chapter, yeah, debate a lot of things, but yeah, it's within the content and you should cover it. All right, so we can do a first example. Like I said, this is a fairly easy chapter, and definitely we'll be able to finish it up today. All right, so let me just copy this example, and then we can just get going. Maybe we can do an extra one. We did have an extra one there, so let's just say example one. What page is in the Dosky textbook? Is this a new? Just checking if I have a new. Not sure if I have a blank. Okay, yeah. Switch. Right, so that's example 8.1, I believe. And yeah, so we have a vertical steel rod. We've got some rod. Did you fix it on the top? So just sketch that quickly. Right, something like this. And there's some collar on it. I don't know how to really just sketch a collar around it here. But it's basically surrounding the body so that a weight can basically fall on you. So they're saying calculate the maximum stress, instantaneous extension, strain energy. If I think I included those extra things there. I wonder, yeah, if a weight of 20 kilonewtons, it's gradually applied, suddenly applied, and then basically falls from the collar. So if you remember that models, it's really simple, guys. Remember for gradually applied, we're just going to go to your standard P over A, and that's 20 kilonewtons over the area, and that'll give us 0.025. Okay, right, so we assume it's applied nicely, constant rate, right? Okay, so what do we get here? It's pretty plug and play chapter in our opinion. So what is my stress, my induced stress? U2 was gradually applied. 40.74, yep. I can accept that. So the logic here, guys, is that obviously if the load is suddenly applied now, what are we expecting, right? There'll be more stress increased. That's the idea. And in this case, the model for that was just basically 2 times that value, and you're just going to say 2 times 40.74. Right, just to get you a feel of this. Okay, let's just quickly see. Obviously that should be easy, around 91.49 megapascals. Okay, so I'd like to see you guys to see now, right? So C has a so C has a special equation, if you remember. Can I actually is it over here? Okay, we can use that equation. But yeah, you're going to see when it gets fun because with that you can't just use this equation. But if it does arise, you basically just get. So that's the equation you basically going to have to use to find that. But this is essentially this thing. If I've explained it well, it just comes from this. So your potential energy. So as initial height, it drops. There's a change in length, and it's squared over 2e. And if you play around with these values, you're basically going to get this formulation over here. So let's just quickly get those values. A very quick example. Yeah. Very simple chapter. Just got to plug and chug all of those. So the load is 20 kilonewtons times 4. Well, we have that value there. So pi times 0.025 squared. So 1 plus, remember we just get out the tensor one according to this. That's 1 plus 2 times the area. I'm not going to write that in. Let's fold from I to 0.05 times 200 divided by the load, 20 times the length of 6 meters. Right, so you get two values there basically. So one will be tensile and one will be compressor. Okay. So as you can see, it's, yeah, because we have season parallel coming up next, so that's where it gets a little more fun, I guess. Someone just get me those values, can someone just work it out to get a feel for it? And we're gonna work out the instantaneous. We're gonna look at the extensions and the strain energies. So I think I included that there. So, yeah, I know we've got that already. Looking at the basically it's the impact load now. Yep, that's correct. I'm not sure. It can't be gigapascals, man. It's impossible. Yeah. Could be, yeah, 401. 411, sorry. 5, 6. A state solid state there. And of course, yeah, there we go. And then we have a compressor one as well. It's gonna make that negative. And this should be around 330, I think. Megapascals. All right. So, guys, just to extend the problem further now, what I want us to do is work out. So I'm going to say number 2A is work out our, yeah, let's count the zeros. I see. We just have to work out 2A to B to C, just the change in lengths, right? Basically due to this each respective stresses. But obviously, what we're going to find is that we don't really have to do this, but obviously on this load here, on the impact load, this is going to be the highest. So that's what's just important on that. It's gonna for 2C, it's gonna the deflections, we could call that X. It'll shot up, it'll go up, and then eventually do this. That kind of thing. It's a big deflection, and then it essentially settles. So you have a big change of length. And obviously to work out the strain energies, and maybe it's just kind of obvious, really a waste of time of doing it. I'm looking at it now. Times the volume. You obviously find, because this value is bigger, how much strain energy you actually getting within the body. And if you compare them, you'd obviously see that if you'd have a higher one on a shock load as compared to as a applied suddenly, or so-called live load, and then the gradually applied load. So it's not really worth doing, but I just thought I put it there some time ago just to kind of have a comparison of the two. But I think it's fairly self-explanatory in terms of that. Okay. We can do the next example, and then I have one where you guys can actually and then yeah, that's like a student guess that's from the textbook, and maybe we can solve it. Yeah, go for it.
The change in length in 2C, do we use a compressive or the tensile?
Just the tensile, just the tensile.
Just the tensile.
I'm just getting the instantaneous length, yeah, change in length, yeah. No, the point is just to illustrate the strain energy. It's not really anything fancy. So, but we don't normally consider the compressive one. That's just making you aware. That's normally ignored. Just making you aware of that one. Okay, there's a question Alex gave us last week or 2 weeks ago, but now I'll attend to that question today. But anyway, so next example, we've got a steel bar, diameter 25 mm, 1.22 meters long, 1.22 absorbs a specific amount of energy at its limited proportionality and the actual loading, right? So it's basically at its maximum. It's a maximum amount of energy you can basically absorb. So what they really want here is just to find the amount of stress, or the so-called instantaneous stress, right? Induced within the bar, right? So just we have. So just draws a typical graph. Yeah, so they basically say at this point, just at this particular point, this was 65. They're asking you what is that stress. So what we basically do, we just have to say we know that our strain energy. Then this is the main model, basically 2E or equation times volume. Right, and we know 65. 2 times 200. So if I ever have something in a test like this, the way I'll play around with it is just I'll change materials, and it's not much I can do here. But yeah, just guess it's fortunate. It's easy for you guys to solve. But I recommend solving all the ones in the textbook. Obviously within the scope will be covered here. That'll be the extent of what you know of what is expected of you. So obviously here we got 2 stress values, I think, or 1 stress value. And I can just quickly sort this out. So 65 times 2 times, and then pi over 4 times 0.025 squared times 1.22. I don't think I missed anything, and we can just root this guy, and that'll be the exact stress at that particular point. Okay, so maybe we can just get that answer for everyone. Yeah, 208.36 megapascals tensile. I think it's tensile. And then what they also call for is the gradually applied load, your suddenly applied load, and drop from height of that much. So we're looking at for us to what force do we require keeping the energy constant for these different conditions, right? And obviously we're going to find something interesting, and I actually wanted to reveal itself, right? So the equation, so the energy equation is basically for so this is A, for B. If you did I actually, yeah, so the first one is U equals half PL, and that's how we're going to find the load for the first condition. For the second condition, we remember it's going to be U equals half of, but remember it's 2 times. If you remember, 2 times it's 2 times P. Therefore, times length. I think I'm right here. Oh, this is changing length. Sorry, my bad. It's changing length. So there, 2P, change length. And then obviously we can cancel these guys out to let the speed times that. That is the energy equation for that. And then for this one, which is your U is going to be equal to obviously your potential energy here, which is going to be H plus the deflection. It's very basic concepts here, right? Nothing fancy, guys. So don't worry. It's going to get fancy in the next 2 parts. We're just doing our combined bodies and stuff. All right, so I'll just start the first one off for you guys. So we have, if for us to get for 65 joules, what load do we require? And then obviously now what we need to do is calculate the change in length now. And I can have it here, the change in length due to this stress, which is the maximum amount of stress is this, length of 1.22 over 200. I might get fancy with the chapter, but yeah, can't we just say force over area?
Sorry, can I ask a question?
Yeah, go for it.
These formulas for 1, 2, and 3 there that you have under B for the strain energy.
Yeah.
My internet's been on and off this whole morning. I've been having trouble following, but those equations I haven't seen them before. Are they on the slides that I can go look at later, or are they just going to be here?
Yeah, they're in the textbook. Yeah, you can. It's in the textbook. What you could have also done was like find the stress and then work backwards, but I'm sure you can exactly do that. You're right. So let's see. For the first one, right? Okay. Thanks. Yeah, so you saying can't just use this. You're probably right. Let's see. So what's the force is stress times area? And then we can go to 208.36. I think that's when we can use this as a gradually applied load, obviously, times that area. So let's see what we get. I'm sure we will get it. If I simplify that, I'm sure I'll get exactly what you're saying. I hope so, anyway. Or we can just call it P for now. Now the formulas are all there. It's not hidden. It's within the text. Like I said, it's really not one of my 102.28. Is that the correct answer? Let me just raise my keep on. So you can use that, Jason. It's right. It's the same thing. But obviously they're using the energy formulas because it's supposed to be exactly the same. Yeah, you get the same answer. 102.278. Yep. It's supposed to all work out. That's the point. So we find the change in length here. You get 1.271 times 10 to the negative 3. And yeah, if you just basically have the same load, I'm looking for P and then 1.271. Yep, you should get the same answer. Yeah, I know you guys are probably like, well, what is this? But yeah, that's the next chapter. This is the next chapter, which is good for you guys. Obviously for the second one, I'll just divide that answer by 2 because I know that it's so this is obviously 102.7 divided by 2. That's just working backwards, guys. Obviously, if you take stress over A, stress times A divided by 2. So yeah. Yep, just letting you know. It's all they're just using the energy formulation as opposed to give us the same answers. That's the point. And then yeah, so here we're just gonna go. Obviously, this one we just can't use the same stuff. Obviously, we could have worked another way, but there's something just important to note here, and you see it now. Where was it now? Where am I here? So U equals mg h plus that changing length. So is there a quicker way to do this, Mr. Romanus? Just instead of using your energy formulations, does anyone have an alternative approach? So just quickly sort this guy out. This also should be easy. I'll be looking for this P, by the way. So this is P. We fall into the height of 0.12 plus that elongation. No, so you must use that. I think find the change length in the force. Okay. Yeah. Okay. And then we can just calculate P. Then we can have a small discussion. And then yeah, we can have a break into the next session. Yeah, Shem, it's a problem to do, and then yeah, you will start with that problem and finish up. Yeah, I can't be kilonewtons. It's too high. Yeah, 535.98. 535. Yeah, 535.98. Okay, so just looking at this values, right? Just like to interpret what's happening is that if you suddenly apply a load, right, all it basically means that you don't require much force to induce the same amount of energy. And obviously, when you gradually applying a load to induce an energy of 65 joules, you require a big amount of force, which you're applying obviously over a steady or constant period of time. So, yeah, the point here just is, even though you have a smaller load, you know, if it's coming on an impact, you can still get the 65 joules. So, and what they basically say at the end is that one must be aware of the loading conditions when they actually, when you're basically doing design, depending on the design. So if you're going to be adding something with a lot of impact happening, you know, be cognizant of that. So yeah, that's basically that example. There is another example you can work through. It's 8.2, but that is also easy. You can just go through that one. Then so what I'm going to leave through on the break, so you guys can work through something. Because I know luckily we can finish early today. Is obviously we have to have electrodes, and I'll be solving this one with you guys. So I'm sharing it now. Yeah, so here we have, so you're going to do example 8.5 for me, and we'll solve that together. So this is the one Alex was asking me exactly how we're going to solve it. So I'd like us to solve that one. Probably take us a few minutes, and then we're just going to go into your series members, which is easy, and your parallel members, and also with strain energies, and we're probably going to do 2 more, and then we're basically done with this chapter. Yeah, if you guys are going to be good with it, we can just, you know, don't have to actually just do it, but I'll do it anyway, obviously. But yeah, so what I recommend, go to textbook, go do 8.5, and then I'll be back in the next 20 or so minutes, and then we can just finish up and then I'll see you for, I'm basically seeing you for electros afterwards. Okay, guys. Yeah, see you shortly. I'm stopping recording for this session of, and then I'll come back and record.